Hello, welcome to the first tutorial video on differential equations. Okay, so I am Mexams, and in this video I'll take you through the introduction to differential equations. If you are new to my channel, please kindly subscribe to my channel and click on the notification bell so that in case I release any other video relating to mathematics, you get it first. Okay, so let's start. All right, so what is the definition of a differential equation? So a differential equation is an equation which involves one or more derivatives. So this place is very important. Derivatives. So it involves one or more derivatives or differentials of an unknown function. This part is also very important. So it should be one derivative at this side, and there should be an unknown function at this side. Okay, so that is why we term as, if you have an equation like that, then that equation is what, a differential equation. This means that if you don't remember your derivatives very well, you're supposed to go and prepare about derivatives. Okay, all right, so what are the examples of differential equation? Okay, so normal differential equation, as in you can get an equation that involves some derivative and some functions. Okay, something like if you have dy dx equals, let's say, 3s squared. Okay, if I have something like this, then from the definition we have derivative. The derivative is the dy dx. Okay, and that is what, 3s squared in some unknown function. Okay, of an unknown function. So the derivative is this side, and it is the unknown function is what we call what, y. Okay, the y is what we call the unknown function. Okay, so this statement, this whole statement, I'm coming, this whole statement means that this thing means that there was some function. Okay, I'm coming, there was some function y that when you differentiate it, it will give you 3s squared. That is what the definition means. It means that there's this unknown function y that we don't know, like we said here, that when you differentiate, you get what, 3s squared. Okay, mind you, in this you could see that there are other examples that I can give. Okay, I want to give an example and explain some terms here. Okay, so if let's say I give this example as d squared y, sorry, this is not nice. I'm coming, d squared y ds squared, okay, is equal to say negative k squared y, okay, minus, let's say, 2x. Okay, so in this equation you could see that there is an x here and there is what, a y in this. Okay, so quickly let's define the terms x and y and you will know them. Okay, so if I have a differential equation like this, and there is an x term this side, the x here, and there is a y term, this is what we called, this side, the x is called what, the independent variable. Okay, independent, and the y is called the dependent variable. Okay, so take note of these. Okay, so if you have a differential equation like this, then your y in the equation is called the dependent variable and your x is called the independent variable. Okay, so that is it. All right, let's continue with the introduction. Okay, so let's talk about classification of differential equations. Okay, so you have to know how you go about differential equations. If you are given, let's say, a differential equation, what type of differential equation is that? How do you classify the differential equation? Okay, so if you want to classify differential equation, there are 4 ways of classifying a differential equation. So you can classify a differential equation by either type, that is either being an ordinary differential equation or a partial differential equation, or you can classify a differential equation by its order. or the degree or the linearity. Okay, so let's say these parts, I want you to take them seriously. All right. The linearity. Okay, how do you know that a differential equation is linear? And also the degree and the order. Okay, how do I know the order of a differential equation? Okay, so these three, they are different, but it comes with, this one comes with its definition. Okay, so how it is being written, when you see it, the moment you see that, oh, this is an ordinary differential equation, or this is a partial differential equation. Okay, so let's take them one by one and start explaining them. Okay, so classification by type. So if I want to classify a differential equation by its type, we said another type, we said we have what, either ordinary or partial. Okay, so let's say we are classifying them, and we have what, the ordinary differential equation. Okay, ODE, sometimes called ODE. We are saying that an ordinary differential equation, ODE, is one containing ordinary derivatives of one or more unknown functions, that is the dependent variable that we said earlier, with respect to a single independent variable. Okay, so here the independent variable can be one or more, but the dependent variable can be one or more. Okay, I'm taking that part again. We are saying that the dependent variable, this side, okay, can be one or more. Okay, but the independent variable, which is normally termed as x, is just one. It's a single independent variable. Okay, that is an ordinary differential equation. So an example of this type is, I'll give one that the dependent variable is just one, and I'll give one that the independent variable is many. Okay, or are many. All right, so let's see. The first example is, if I have an ordinary differential equation, something like dy dx plus 2xy is equal to 0. Okay, this is an ordinary differential equation because we have what, just one we have just one independent variable, and we have, okay, the dependent variable is just y, and it can be many. Okay, so let's see a case where the dependent variable, they are many. Okay, let's consider something like the Cauchy-Riemann equation in complex analysis. Okay, so if you have an equation like du dx equals dv dy. Sorry, I'm coming. I'm coming. I think the Cauchy-Riemann equation wouldn't work for this. So let's say this, which will yield du dx minus dv dx equals 0. So what this means is that I have two dependent variables that are what, u, the dependent variables are what, u, that is this one, and v. Okay, those are the dependent variables. Okay, so if let's say I see something like this in an equation, then this means that this is what, an ordinary differential equation. Okay, just put it in mind. Okay, all right, so let's continue with it and go to the next one. So partial differential equation. Okay, so a partial differential equation is one involving partial derivatives of one or more dependent variables with respect to one or more of the independent variables. Okay, so here the dependent variables can be many, and also the independent variables can also be many, like they are also many. Okay, so the dependent variable can be just one of them, but the independent variable should be many for it to be partial differential equation. Okay, so let's consider an example like the Cauchy-Riemann equation that I stated earlier, that if I have du dx equals dv dy. This is an equation from complex analysis called the Cauchy-Riemann equation. Okay, and this is an example of a partial. Sorry, it should be del. It shouldn't be d. Okay, it shouldn't be d. For partial differentiation, we use del something. We don't use just a straight operator d. So it should be del u del x is equal to del v del y. Okay, and so this is what you call a partial differential equation. I can also get something like coming. I can also get something like del squared u del x squared plus del squared v del y squared plus, let's say, del q del t. So you can see that the dependent variables are how many? 3 of them. We have v here, you have u, and you have q. All of these are dependent variables, and we have the independent variables to be what? 3 of them as well. So with this, we say we have a partial differential equation. Okay, so based on classification of differential equation by type, then you are supposed to see that either the independent variable and then the dependent variable are many, and the condition is that the independent variable should be what? Many. Other than that, you have an ODE, an ordinary differential equation. Okay, all right. So continue with the classification by order. Okay, with the classification by order, how do you say that this is the order of a differential equation? You are supposed to know the definition of it. You are saying that the order of a differential equation is the order of the highest ordered derivative appearing in the equation. So in other words, you can also say that if I have a differential equation like this, dy or the cube y the s cube plus the squared y the x squared plus, let's say, dy dx plus 2y equals 0. So here you check what is the highest order, or why is the highest derivative here? Is the third derivative, right? So the order of this differential equation is what? It is with order 3. Okay, so the order is 3. Okay, all right. So with this, we are saying that the order is 3. It means that if I have a differential equation, something like, let's say, dy dx equals 2x, with this differential equation, the order is what? Is with order 1, because the highest derivative that you can find in this whole of the differential equation is what? 1. Okay, so that is what it means. It means that if I have a differential equation, then if I want to find the order of the differential equation, I need to make sure that I just find the highest derivative in it. Is it the third derivative? Is it a second derivative? Or is it a first derivative or the fourth? Okay, so the highest one in it is the order of the differential equation. Okay, so let's continue. All right, so classification by degree. Now here is the problem. Okay, here is where the problem starts. How do I know that the degree of this differential equation is, let's say, 2, 3? This is simply put, you are saying that the degree of a differential equation, this one, is the power. Look at it very clearly. The power of the highest derivative term. The power of the highest derivative term. Okay, so the power of the highest derivative term. So looking at this, It means that if I have a derivative like this, let's say d squared y dx squared plus, let's say, dy dx plus y equals 0, then this, with this, what is the power, what is the higher derivative term here? The highest derivative here is the second derivative, that is the squared y dx squared. And with this, what is the power of the whole of this? The whole of this thing is what? 1. So it means the degree of this is what? 1. Okay, that is it for now. Now let's check this. If I have the cube y dx cube, sorry, plus dy dx all to the power 5 is equal to, let's say, 0. What is the degree of this differential equation? This one that I just wrote. What is the degree of it? The degree here is what? If you can see, we are saying that it is the power. Look at this side, the power of the highest derivative term. So looking at the highest derivative term here is what? The cube y ds cube. The power of the whole of this differential equation is what? 1. So the degree here is what? 1. Okay, I hope this is clear, right? So if you have something like let's say the squared y ds squared all to the power 3 plus dy dx equals 0, then with this, the degree is what? We are saying the degree is 3, because the highest derivative term in this whole of our differential equation is raising power what? 3. Okay, I hope this is clear. All right, so let's continue with the introduction. Okay, all right, so classification by what? Linearity. I said, if you could see the classification by type, the ordinary differential equation and partial differential equation, they were easy to identify. By classification by order and degree, there were some way. But looking at classification by degree, that, as for that one too, is a different thing altogether. Okay, and classification by how do I put it, linearity, this is where the problem comes, because in this there is a different format that you are going to use to understand it. So you are saying that a differential equation is linear if it can be put in the form. So I'm coming to write a form for you, okay, so that you know that if you meet any differential equation and it is, sorry, if you meet any differential equation and it is in that form, you can see that, oh, actually this is a linear differential equation or not. Okay, so if any differential equation given can be rewritten as, or can be written as an of x y to the power n. Now I will explain this later. Plus an minus 1 y to the power, I'm sorry, this, you should put in mind that this an minus 1 is what? A function of x. It's a function of x, right? Y to the power n minus 1, then plus dot 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 plus a1 y prime plus a naught y equals what? 0. Okay, so if, or it can be equal to an f of x or anything. Okay, so let me put it there. Okay, and let's say this is actually equal to, this is equal to f of x. Okay, so if you have something like this, okay, then this is what we call a linear differential equation. Okay, so an example is let's say like I said, let me explain these things, these terms, y to the 4 something, y to the, so another way of writing, let's say dy dx, you can rewrite this as what, y prime. Okay, so d squared y, sorry, I think my handwriting, I need to do something about it. Okay, so d squared y, the s squared, this will imply what, y prime prime. So it means that this y to the power n here implies that we have, sorry, implies that we have what, the nth of y, the nth derivative of y with respect to what, x. This is what this implies. Okay, so that is it. So let's look at an example and everything will be okay. Okay, let's look at some examples. So if you are given any differential equation, just check that, can I write them as what, summations of these, and if that is possible, then we have what, a linear differential equation. So an example is 2x y prime prime plus 2y prime plus 6x equals 0. So this, looking at this, the whole of this is what, a linear differential equation, in a sense that I can put the whole of this in at the other side. Okay, so I can write this as what, 2x y prime prime plus 2y prime is equal to what, minus 6s, and this minus 6s now becomes what, f of x. Okay, I hope this is okay. So this is what we mean by a linear differential equation. You can get something like 2y, sorry 2y 2y plus, let's say, 3 dy dx is equal to 0. This is also a linear differential equation. Okay, so those are the those are what we call linear differential equation. How do I know that this differential equation is linear? Okay, so let's look at them. So conditions for a differential equation to be linear: one, we have the first condition saying that the dependent variable and all its derivatives occur only in the first degree or to the first power. If you remember, we said the degree of a differential equation is what, the power that the highest derivative in the differential equation raises to. So something like, we have d squared y, the s squared plus, let's say, 2y equals 0, then it means that the power of this whole thing is what, 1. So we said the power of the highest derivative in this is what, d squared y, the s squared, and the power is what, 1. We are saying if the power is 1, or if it is of the first degree, then we are saying that this differential equation is what, linear. Okay, that is for the first condition. Now the second condition is saying that no product of the dependent variable, say y, and or any of its derivative present. No product of the dependent variable, say y, and or any of, so underline word is what, the dependent variable, that is this y that we are talking about, and any of its derivatives. Okay, so let's look at this. If I have something like 2y dy dx plus 3y equals 0, is this linear? No, this is not linear, because you have a product of what, y, and the dependent variable here is what, y, and we have a product of the y and its derivative, that is this side, okay, being present in this whole of our differential equation. Okay, the equation 1, we have a product of what, the dependent variable y and its derivatives. Okay, and this is when we say this is not a linear differential equation. So for this to be a linear differential equation, there shouldn't be any y here. I hope you get it. And now this whole thing becomes what, a linear differential equation. I hope this is okay. So let's continue. No transcendental function, that is, say, trigonometric, logarithmic, or exponential of the dependent variable and or its derivatives occurs. Look, we are trying to say that the underlying word is what? The what? No transcendental function. So these functions, any of these of the dependent variable, that is this side, and its derivatives are present. So let's see this equation. Dy dx plus 2 sine y equals 0. Is this a linear differential equation? No, because we are saying that for this to be a linear differential equation, there shouldn't be any sine, that is trigonometric function. Sine is what? A trig function. There shouldn't be any sine or cos or tangent or secant or cosecant or what? Cotangent of the dependent variable, which is the y, being present of the differential equation. Or there shouldn't be any transcendental function, that is trig, logarithm, or exponential functions of either this dependent variable or its derivatives, okay, being present. So if this is what? Not a differential equation, a linear differential equation. So if I want this to be a linear differential equation, then it should have been something like dy dx plus 2 sine of what? X equals 0. I'm sorry, okay, I'm sorry, kindly forgive me for that. Let's continue. Okay, so this it shouldn't be a problem for us. So this is what? A linear differential equation based on this definition. Okay, I hope you understand it, and I know you would really understand. Please, like I said, if this is your first time coming to my YouTube channel and watching a video on my YouTube channel, kindly subscribe to my channel, because you have more to do on this channel. Okay, all right, so let's continue. Solutions to differential equations. Okay, now let's look at the definition of it. We're saying the solution of a differential equation is any function. There are some words that we should underline here. Solution of a differential equation is any function, okay, say file, that satisfies this word is really important, that satisfies what the given differential equation on a specified interval, say u. Okay, on a specified interval, say u. Okay, so you given this differential equation, okay, I'm coming, given any differential equation, all right, any function that given any solution of a differential equation, then that solution should satisfy the given differential equation. Okay, so show that the following functions are solution to the given differential equation. So I'm going to write some differential equations here, and with them we'll just try to show that they are actually solutions to the differential equation given. Okay, so let's start with them. Okay, I have the first differential equation being that, the first differential equation being d squared y dx squared plus y equals 0. So let me write it down. Okay, d squared y dx squared plus y equals 0, and we are saying that the corresponding solution is file, which is equal to c1 cos of x plus c2 sine x. I'm coming. Okay, let me erase it and write it well. Okay, So like I said, you are saying that the corresponding solution that we are saying is a solution to this differential equation is c1 cos of x plus c2 sine of x. I think I have to do something with my handwriting, okay? Please pardon me, okay? But follow me. If you follow it clearly, you will really understand. Alright, so with this, from this equation, we are saying that with this function, so file is actually a solution to this. It means that I can say that file is what equal to y, which is the unknown function in this. So if that is the case, then it means wherever I see the squared y, the s squared, I have to differentiate file how many times? 2 times. Okay, so then I have to find the file. Sorry, I have to find the file, the s, which will correspond to the y, the x, and this is equal to what? When differentiate cos, c1 is a scalar, so when differentiate cos, you get what? Negative, then the scalar will come, then what? Sine of x, then plus c2, and differentiate sine, what will you get? Cos of x. Okay, so that is it. Now what will be my second derivative? The squared file, the s squared, is the same as what? The squared y, the s squared, and this is equal to, when you differentiate this side, sine, you get cos, but there is a negative, so we maintain the negative c1 and cos x. When you differentiate cos, you get what? Minus, so minus c2 sine of what? X. Now this is the squared y, the s squared. So from this whole equation, we come and put everything here inside the squared y, inside of the equation. Where we see the squared y, the s squared, we put it there. Then where you see y, we come and put this phi there, because you're saying that if phi is a solution to this, then the solution is what? The y, that is a dependent variable. Okay, so we put it there. You put y, which is equal to this, back into the equation. Sorry for this. Like I said, you just put y, which is equal to the file, back into the equation, and the squared y, the s squared. So if I put everything, it will be like minus c1 cos of x minus c2 sine of what? X. I'm putting the whole of this side into this equation again. So the squared y, the s squared, is equal to this. I can mark here. I put it back there, and if I put it back, it's like minus c1 cos c2 cos s minus c2 sine x. Now then I add it to what? My y, which is equal to phi, and that is c1 cos x plus c2 sine of what? X. If I add the whole of this, negative c1 cos s plus c1 cos s, this will take this away, and this negative c2 sine x, then plus c2, this will also take this away, and at the end the resulting solution will be what? 0. So we are saying that this side, after putting everything there, we had 0 to be here. And it's true, because we are saying that if you differentiate the solution of this differential equation 2 times and add it to the actual solution, you will get 0. And indeed, after differentiating it 2 times and adding it to the actual solution, we had what? 0. So this means that this whole file thing, this side, is actually the solution, is a solution to this differential equation. Okay, so we are done. Okay, so let's look at another example, and then you really understand it well. Okay, all right, so with this, let's look at it. If you have a differential equation given as x y prime prime y prime prime plus y prime equals 0. So what this equation means is that if there is a certain function that if I differentiate it 2 times, multiply it by x and add it to the first derivative of the function, I'll get 0. This is what this means. And we are saying that this function y being equal to ln of x is a solution to this differential equation. Now, if this is true, we are saying that this is a solution to this on the interval I equals the open interval -1. I equals I equals 0 and infinity. Why? This solution is true. This is true because before we continue, let's look at this. We are saying that this solution here, y equals ln x, is only this y equals ln x is only a solution for this within this interval and no other interval. This is because if I'm coming. This is because if we are to solve for the values of x, or if we are to plug in values of x of this solution given, that is the y, if we are to put values of x here, logarithm ln is a logarithm, and we are saying logarithms are not defined for negative numbers. Log of 0 we don't know. Okay, so for that matter, this solution can only be defined within the interval, the open interval 0 and infinity. Means 0 is not part, infinity is also not part. Okay, so only values between them. Okay, so ln of 0.0001, this will work for it. Ln of 0.01 will work for it. 0.02 will work for it. Ln of 2 will work for this. So that is why we are saying that this is a solution to the differential equation within the given interval. Okay, so let's try and see if what they are saying is true, or what we've been given is true, that this y equals ln of x is actually a solution to this differential equation. Okay, let's do this and we'll really understand the solution to a differential equation. Okay, now y prime prime means that what you are supposed to differentiate a thing 2 times. But before you differentiate something 2 times, you need to do what? Differentiate it for the first time, then you take it from there. Okay, so y prime is equal to, when you differentiate ln of x, like I said in this course, if your differentiation is very weak, please kindly go back and do recap on differentiation. I have a video on the derivatives of logarithms, trigonometric functions, and also some polynomial functions as well, so you can search in my videos and then you get it. Okay, so y prime from ln x, if I differentiate this function, what do I get? I get 1 over x for just ln x. Okay, then y prime prime is equal to, when you differentiate 1 over x, is the same as differentiating x to the -1. Okay, finding this y prime is actually equal to, the y prime is actually equal to x to the -1. So if I want to differentiate this, that is y prime prime will be equal to, we said you just do what, multiply this power, the power of the function, the parent function. So y prime prime means you are differentiating y prime, so you are just multiplying the power of this parent function, that is this side, in front of here. Okay, and that will be -1. Then we subtract 1 from the power. Okay, so we can -1 x to the -2, and from indices y prime prime will be equal to what? negative 1 over hot s squared. So from this, it means that if I put this here, everything, this y prime prime and y prime, these two, if I put them back into the original differential equation, I should get 0. That is what this means. So let's try and put y prime prime there. So we have in the original equation, you have x times y prime prime, which is what? Negative 1 over hot s squared. And we have plus y prime, which is what? 1 over hot x. And this will yield x times that. One of the x will cancel this s squared. One of the s squared will cancel this x. Okay, so we'll be left with negative 1 over x, then plus 1 over x. And I have negative of the same thing here plus the same thing. I'll get what? 0. So since this is satisfied, this condition that we are saying that if I put everything back here I should get 0, this is satisfied. It means the solution y equals ln x is actually a differential solution, the solution of what? X y prime prime plus y prime equals 0. So this is true, and since this is true, we are saying that y equals ln x is what? A solution to the differential equation. Thank you. And so I'm urging you that if, once again, this is your first time of watching my video, kindly subscribe to my channel, because we have a lot to do. And subscribe and turn on the notification bell so that in case I send or I upload a new video, you get it first and understand mathematics for the entire class that we have. Okay, so thank you and see you next time.